Hi, my name is Zach Robinson. I'm the general manager of Western Thermal Processing, the home of the Precision Quincy and Infotral industrial oven brands. And in this video, I want to talk about our philosophy on how we deal with forces and stresses due to thermal expansion of the metal or materials in our ovens. And so this philosophy is, we call it zero stress. It's developed over I'd say probably like 7 to 8 years of looking at our previous designs and our competition's designs and seeing, well, where's the weaknesses that they have that cause these ovens to wear out faster. Because it is common knowledge that higher temperature ovens, anything over like 500, 600, 700 degrees, they start to have problems with cracking and things like that. Our ovens do not seem to have that problem because of this philosophy. And so instead of designing an oven in a rigid way and then dealing with warping when we find it, we design stuff so that there is no stress built up, so warping is almost impossible to happen. An example of that is the way we build our conveyors, the way we build our internal structure on our ductwork. All of our can constructed ovens are all following the same principles of zero stress due to thermal expansion. So the easiest way to explain this is, if you have, let's say you have a pipe. None of these markers show up very good on the video. Okay, that one's probably pretty good. Let's say you have it's like a 1-inch pipe, and it's in an oven, and so it's going to grow. If it was mild steel, it would grow 7.8 times 10 to the negative 6th. If it's stainless steel, it would be like 9.8 times 10 to the negative 6th growth in inches per degree temperature per inch. So sometimes this could be 6 inches inside of an oven of growth, and you really don't want the outside to move at all. So you're going to have this huge stress built up, which is strong enough to bend 1/4-inch steel, and it can literally destroy an oven. That's pretty much the main cause of ovens getting destroyed, is built up thermal stress caused by thermal expansion. So if you just had a pipe sitting inside of an oven and it was just sitting on some fixture points, I always show gaps in there so you can see it, but it's actually sitting on top of that. This thing's going to grow this way and this way. It's also going to get a little bit bigger. Well, let's say we pinned it right here. Well, then it's only going to really grow that way. This will grow a little bit, but we have still created almost no stress caused to that thermal expansion. If when it's cold, we decided to pin this right here, represents a screw, then now we're going to cause this force that is pushing. The screws are pushing this way, this is pushing into that, and so as that force grows, eventually it's going to cause this pipe to buckle. At lower temperatures, a lot of times the internal stiffness of this pipe, or where we put it, is strong enough, the resistance to buckling is strong enough that you're not going to have any kind of warping. But once you get into higher temperatures, like over 500 degrees, probably definitely in the 800, 900,000 degree range plus, if you were to put a solid piece in the pin on both ends, you're going to have a lot of warping. So the thing would actually go like this. The pipe would end up being like that. So, if this is just a single part inside that, what's it going to, it's really not going to affect the structure of the oven, except for it's going to put forces, in here. So instead of bending this, maybe you're bending the entire oven. Some kind of structure on the bottom of the oven, but if it was very rigid, you're going to end up destroying this part over time. Sometimes instantaneously to destroy it. So when you're talking about get some cleaner on this thing, but when you're talking about let's just say the construction of a industrial oven, and you're looking at many times ovens are very much like a box. So let's say that's your oven. So you have a door in the front, and you have, you know, this side, in the back. The floor is usually, a lot of times we'll make it just float in there. Sometimes you put concrete down. There's a bunch of different ways to do the floor, but all of it has this desire. If this was the inner, let's just say this is the inside, and it was exposed to 800 degrees or whatever temperature it is, it's going to want to grow out in almost every single direction equally. So that's going to cause this thing to want to move like this, and then when it cools back down, it's going to go like this. The thing about it is people don't like their whole oven sliding across the floor, nor can you do that because you have weight in there pinning it down, or some kind of conveyor loading or anything like that. It's connected to utilities and all these things like that. You do not want to have the oven sliding across the floor in a significant way. It will slide a little bit, but if you were to pin it down in all four corners, what would happen is the thing would actually bow up and lift itself up off the ground and tear any of the studs that are holding it to the concrete down. So if it's a, let's say 800 degree panelized oven, which doesn't have a separate inner and outer shell, we just pin it in the front of the oven and we let the back grow and it slide a little bit, but it's not really that huge of a deal. But let's say most of the time you just want to pretend like you can't do that at all. So there will be some little bit of growth, but it's usually, we want to keep that to a very small, like under a quarter-inch number or something like that. So if you have this inside and you put insulation around, and then you want to have the outside not move at all, you're basically creating this this balloon inside of this box, and if that force becomes strong enough, it's just going to push those walls out. So you'll see some ovens, people's ovens, where every time it gets hot, the oven's moving around a lot, it's picking itself up off the ground, and that's because all this force from the inner shell, there's nothing in here to let the oven move at all inside of itself. It has to force itself out. So you can overcome that with a really, really rigid outside of the oven, which you want to have anyways, because this is going to push out. But let's say you pin these points, and you want to say, I don't want them to go out at all. They will move, but let's say you just said they can't. What we do is we will take that and I'm going to move this to a single plane instead of looking at it like this cube. And let's say we're looking at the side of an oven wall. And so we do the same thing on all of our ductwork and everything like that, but just looking at the shell of the oven. If this was going to grow, let's say 2 inches, if it was zero restraining it. Now, I don't want to go into the exact numbers I use because it's kind of our secrets, but if you were to say, okay, I want to make it so that this point can't go anywhere, this point can't go anywhere, this point can't go anywhere, and you just divide it right down the middle, and you put a 2 and like a 2 1/4 inch gap in there. Sorry for the horrible drawing, but this thing is going to fill that gap. So when the oven is hot, if there was no resistance to anything moving, there would be a 1/4 inch gap in there, and that would cause it so that there would be very minimal stress pushing on these pins, which means these points, and this would not balloon up. Now, obviously, we don't have that big of gaps in our oven. Something moving that much would cause all kinds of other problems. We have a significantly smaller amount of, or significantly more spaces for expansion and contraction. So you can't have gaps in ovens because you'll have insulation just blowing out on people and their product, which is bad. But let's say, let's just, John here will just explain how we do this this gap, how we let that gap happen, exist on a can constructed oven. And so something that's smaller, like it's only like 2-3 feet workroom area, it won't have any of these gaps because that number is not going to cause a huge amount of movement on the outside of the oven. But if you were looking at let's say this wall, if you're looking at it from the top, on the bigger ovens, we will, let's say this is the outside point, and we don't want that to move. And so we go all the way over here, and we have this point. We don't want this to move. And how we do this is we'll put instead of having this be a perfectly 90-degree bend, maybe we'll make it 80. I don't want to talk about all the exact numbers, but where this thing connects, then we'll have another same kind of expansion joint basically down here. So these will be pinned together. So this does not mean that once the oven gets 200 degrees, you're going to start seeing this gap close down. Our ovens, the interior construction it's on the, most of our proposals, but let's say it's 16 gauge. This thing will not take up that full gap, even close to it, but at higher temps it will start to close that gap down. And it's not always huge amounts, but it's enough to make sure that you don't build up this huge force, which causes this whole thing to bow. And then you have ductwork inside of the oven getting destroyed. And one of the big things that people don't realize a lot of times is the oven doesn't grow at the same temperature, so like the ductwork's gonna get hot a lot faster than the outside of the oven. So you have to attach the ductwork with a plan on that basically the inside of the oven is gonna be 70 degrees or something like that. So as the thing gets hotter in stages, it still has that room to grow. And then when it comes back down, it has that room to basically contract without having this built up stress in the oven left over from the thing getting too hot. So the first time you build up the oven, heat up the oven, you want to go really slow, and then the thing will kind of break itself in. A big thing that people don't always realize is that once you get past 600 degrees, steel strength goes way down. So the things that seem like they might not want to bend, or they might be really stiff, at higher temperatures, they're going to be softer. Like if you take aluminum and you put it on a conveyor belt at right before its melting point, it'll be like Laffy Taffy. It'll want to stick to the conveyor. So this metal does soften up, but even with that, we need to have that room for expansion contraction. Even though we're not going to necessarily use all of it, we always plan on basically having to use all of it. By doing that, we'll make sure whenever we get into a problem where we underestimated how much expansion contraction we needed. So, you don't want to pick, in my experience and what I try to do is, let's not pick a number that we think is going to work just to get a little expansion contraction. Let's make sure we take care of all possible expansion, even though we know that it's not going to, this part is got its own stiffness, it's not going to actually use all of that. And so the way we build the oven, there's connection points and the gaps are set up by a certain formula that we use, but by doing that, everything is constructed where the thing can move, but actually the outside of the shell of the oven is really not going to move into the inside shell of the oven is not going to really move into the outside shell of the oven that much. And so by doing that, you don't destroy the insulation, getting it compressed and all sort of stuff like that. It will move around, but it's not even close to what it could be if it didn't have this in there. We do make some ovens without these if it's small enough, but typically it's the best to keep that in there. The one thing you do lose is a little bit of insulation thickness, but we have our thickness compensates for that. So it distributes let's say this is the outside of the oven. You do get a little closer right here, but you will not see a hot spot on the outside of the oven due to how much insulation we use and the type of insulation we use. And so we'll have this very rigid outside structure reinforced with typically called buck stays or structural steel, and that's going to cause this shell not to move around. The inside can move a little bit, but it's going to grow inside of itself. Ductwork will be attached to this in ways with slots and screws that we use that let the thing grow. So you could have an oven heat up, cool back down. You'll never be able to tell that it got hot. The only difference you'll be able to see is the color of stainless steel. If it's aluminized, you really won't tell it. And so, people are happy when they get like 10 years out of an industrial, high temperature industrial oven. Our goal is to make it so it never fails. And so, that's the way we're doing it. Another thing that we have that's kind of unique compared to other people, the way our processing, our material processing with our laser and press brakes allows us, instead of using like one big sheet of steel and then having stiffeners welded to that on the inside, you can do a bunch of different ways. Our way of doing it is these stiffeners are attached to the inside shell completely through the whole thing, so no cracking of welds or anything like that, which is a typical problem where the inside sheet, I've seen it on many people's, many companies' ovens, the inside sheet will separate itself from the structural steel, and then you have this whole inside sheet that wants to fall down, especially if it's in the roof. The whole thing's gonna fall down. We also have, on the roof, this will be taller to compensate for any strength. And so then some really big ovens, if if we're gonna span a long distance, this is getting extruded out, we will be hanging certain points from the ceiling with still room for growth, so that there is support, but there is no necessarily a huge amount of a chance that this thing can detach from any of the structure that's in the oven. So we do the conveyors the same way. If if you had conveyors, are even more critical for not having the outside to move. If you had a 25-foot long conveyor, a lot of times you have entrance conveyance and exit conveyance, and those you can't really have the oven conveyance move, or it's gonna touch that or push that. And sometimes you can do things with it which simplify the conveyor, but a lot of times like a flat wire belt conveyor, the slider bed that it's on will do the same kind of thing where we break these up and then we'll like support it, pin it only in the middle. If you're looking at it from the top, these gaps are drawn bigger than they are. You pin it in the top, and then you'll just stop it from spinning on that pin by having some kind of restrictions on the outside. And then there'll be obviously some structural steel that this is sitting on, so the thing can grow. And then down here, you'll just support it so for loads going this way, but really there's nothing, there's no point that's rigidly pinning it to anything else except for the center. So one of the big things you want to do is not pin something in an oven rigidly in two spots, because then you're going to have problems with warping and things like that. So there's more stuff to go into, but that's kind of a good beginner of our zero stress philosophy that we use on every single thing, our doors. And yeah, it's a little more complicated to actually make it, but the ovens last a lot longer. So thanks for watching the video.